Thanks. So this is joint work with Mingde Chow, who's he's an undergrad who's graduating this coming year. I think he applied broadly for PhD programs. He's really excellent. So feel free to admit him or not. But I will you know, if you guys don't admit him, then he'll come to me, and I'll be happy. Okay, so he couldn't make it to give the talk, but he would have otherwise. So let me tell you the kind of practical motivation behind this problem and see if you guys buy it. So this is a problem that you know, all of the big you know, Google, all the big phone companies are doing now. So you want to be able to autocorrect or maybe autocomplete some phone text messages. Okay, and this is a distribution learning problem. So given this, you know, text message with this mistyped word, you want to you know, figure out how to do the autocorrection on this. Okay, I'll you know, blah, 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 you in 5 minutes. Maybe it's call, meet, see, so on. Or maybe you're trying to do the you know, next word prediction task. And you know, this is a distribution learning problem. Okay, so why is this an interesting distribution learning problem? Well, you know, your data on which you're going to train is provided by you know, 1 billion different users. Each user has a phone and is submitting you data. And so why is this interesting? Well, you know, there are a very large number of users. Each user is providing a small data set. Each user, though, provides too little data for you to learn their model kind of in isolation. So you need to combine the data among you know, all these different people, all these different users. However, you know, the users might be, you know, they might not all be the same. They might be heterogeneous. Okay, so you know, some users have like a big tablet, and the typos you make on a big tablet are different from the typos you make on a tiny little whatever. Some users might have weird keyboards. Who knows? Okay, so in this talk, we're kind of going to focus on the following. So there's this, you know, so far unexploited, but presumably fairly real vulnerability to training on maybe some maliciously contributed data. So if you think back to, I don't know, 2005, 2006, something like that, there were all this talk of Google bombing or link bombing. This maybe culminated in, you know, for a few days in 2007 maybe? No, 2004? I don't know. Anyway, if you Googled miserable failure, the top hits were links to George W. Bush's page, right? So you could easily imagine that once people you know, realize that, oh, our automatic text prediction is learned on data provided by all the users, all you need is enough users to start doing some funny things in their phone, and now everybody ends up with some weird profanities popping up as their suggested text, right? This is not an inconceivable thing that might happen, right? So, okay, so this picture of you know, lots of users, each providing some modest amount of data, this has gotten a lot of attention recently under the kind of guise of federated learning. So how many people know the buzzword federated learning? Okay, probably next year, maybe all of you will raise your hand, who knows? The Google research blog had a whole thing about this federated learning. It's a very interesting setting. It's interesting both from a learning standpoint as well as from a security standpoint. So people are wondering, you know, how can I use multiple users' data, but in sort of a private way? So, you know, I don't want you guys knowing my data, but to train the models on your phone, you probably need a bit of my data. How can we do this while preserving some privacy? There are lots of questions related to this having to do with, yeah, privacy. Here we'll focus on just the kind of robustness questions. There are also lots of questions related to communication, for example, right? So, you know, how do I, you know, without beaming everyone's data all over the place, how do you train these models while you leverage the fact that you do have lots of different data sets? Anyway. Okay. Okay, so what's the formal model we'll think about? So formal model, so we have M data sources. Think of M as being 1 billion. So this is each person with a cell phone is a data source. Say 1 minus epsilon fraction of them are each going to provide at least k, say, independent samples from some distribution D. Okay, and this is the distribution that normal people have for the word that follows, you know, I will blank. Okay, and then as in Jacob's talk, we're going to make no assumptions about the data provided by the remaining epsilon fraction of our sources. Okay? And the goal is to learn this distribution, say in terms of the total variation distance. Okay, so we also consider the following, which is a slightly more practically relevant generalization of this, which captures the kind of heterogeneity of the users. So say a 1 minus epsilon fraction of the users, each of them provide at least k independent samples from some distribution, but the distribution that I've sampled from might be a little different from the distribution you sample from, and so on. So all of these kind of good users, they each provide independent samples from some distribution whose distance is at most gamma from our target D. And again, how do we return, say, approximation of D? Okay, so is the formal question reasonable? Yeah, is it clear? Okay, and I think at least in this case, this kind of formal question actually is very close to the specific practical problem that these phone companies, Google, and so on, would like to solve. Okay, so again, so think of M, the number of data sources, as being very large. 1 billion people have cell phones. The amount of data that each person provides, K, is kind of modest. Maybe it's small constant, maybe it's 100, 1,000, but so K is small, M is very large. Okay, so the first observation, so suppose K is 1. So suppose everyone just gives you 1 sample. Then no matter how much data you have, sorry, that should be even for large M. So no matter how much data you have, the best you could hope to achieve would be recover your distribution D to error epsilon plus gamma. If everyone just gives you 1 sample, there's no way of figuring out what the good stuff is, what the bad stuff is. There's nothing you can do. So the question is really, how does the error, how could you hope that it decreases as your batch size increases? Okay, so the theorem, so informally, we'll give the formal version in a second, is that as your batch size increases, your batch size is k, the error decreases as epsilon over square root of k. And then, of course, in the case where all the good people have different distributions, yeah, you need to pay your additive gamma. Okay, so the error of recovery decreases as square root of the batch size. Okay, so why is this kind of surprising? Well, so the punchline is that, yeah, you can leverage this batch size even when the batches are far too small to distinguish which data sources are good and which are bad. Okay, so recall that if your distribution D is, say, supported on n elements, well, you might need at least, say, square root of n samples to distinguish whether a given batch is good versus bad. Even if you know what this distribution D is, you might need root n samples to figure out if a given batch is good or bad. So here, even when k is 3 and 4 and so on, independent of the support size of our distribution, we're able to leverage the batch size to decrease the error. Okay, so at the end of the day, we're not going to know which users are good and bad. Maybe some of them we could suspect maybe are bad, but we're not going to really know which ones are good or bad, but we will be able to leverage the batch size. Okay. Okay, so so maybe one point is in contrast to kind of maybe Jacob's talk and a lot of the earlier work in this robust setting, we're really not trying to remove the bad data. Instead, we're just trying to reason about the distribution underlying the good data, but we're really not throwing out any data points. Okay, so we have 2 formal theorems. So the first one, okay, so we pinned down the sample complexity. So the first theorem is information theoretic. The algorithm we get is exponential in the support size of the distribution, but polynomial in the other quantities. Whether you think that's good or bad maybe depends on the sort of distribution you're thinking about. So if the distribution is kind of a distribution over a binary outcome, then that's fine. Otherwise, it's pretty problematic. The second theorem only applies to the case where all the good people sample from the actual distribution D. And there we get sort of efficient algorithm, which is at least polynomial in it's polynomial in n to the batch size. Okay, so if you think about storing each, we'll come to this. So again, this theorem too, it's the algorithm that's interesting. It's a bit surprising for a reason I'll explain in a sec. It's still not what we want, right? We would like a fully polynomial thing, and that's one of the main open questions. Okay, so a tiny bit of context. So there has been at least some previous work on understanding what happens when you have a bunch of batches of data, possibly from different, from heterogeneous users. So there's this work of Levy, Ron, and Rubenfeld, which considers the case where you have lots of batches of data, and you just want to do this identity test. You want to, you want to distinguish the case that, say, all or most of these batches are drawn from the same distribution, from the case where maybe a significant fraction of these batches are drawn from distributions that are kind of significantly different. Okay? And they give very strong positive results in this flavor. There's also some work of Kevin Chen and Wei Hao and myself, where the goal is actually to learn. You're given this kind of very small batches from a bunch of different users, and your goal is to learn the set of distributions underlying this. Okay? Both of these works and all the other sort of related works I'm aware of in this vein do assume that you get IID samples. Okay, so in particular, they're not robust to some adversarial or kind of arbitrary batches. So how much time have I? I've not been. Oh, okay. So the other context of this work is all this, this recent vein on kind of getting reliable, robust, secure machine learning. And just to throw this up there, so they're kind of, so the whole point is, right, the world is increasingly relying on machine learning. We better make sure that things are robust and reliable and so on. There are two veins of work in this area. One is this kind of making sure that what you're learning is robust to bad training data. And this is the flavor of stuff that this talk and Jacob's talk and most of the TCS work so far has been on. There's also this vein of this adversarial examples, which says, suppose your adversary knows your labeling function and is going to give you bad instances that try to embarrass you. Okay? And this is something where the practical ML community has gone mad over it, and the theory community has been is still thinking. Okay. Anyway, I think there are some great problems here. Just to highlight, so there's some work from Don Song's group, which shows you take a state-of-the-art image recognition thing. It's very good at 99.99% of stop signs, pictures of stop signs, it says that's a stop sign. But then you carefully figure out where to put some white tape on it. Okay, so this white tape isn't random. It's been found via your algorithm. And these stop signs now it thinks are U-turn signs or speed limit signs or something like that. Okay, so obviously an issue. And there's been some other work sort of saying that, well, maybe their results seem a little worse than they are. Anyway, lots of good problems I think the theory community should think about there. Okay, so let me just tell you very briefly about what kind of about our results and what goes into them. So again, this is our problem statement. And for the time being, for this talk, let's just assume that all of the good data is actually drawn from this distribution D. Okay? So how to think about this problem? So this is some distribution, say P. So it's a distribution over a bunch of different outcomes. P1 is the probability of the first outcome, and so on. And if you think about what is a batch of K samples from this distribution, well, this corresponds to a point in this K tensor. So this distribution over outcomes you can think about as implying a distribution over batches of size K. So this is n by n by n by n by n K tensor, and the ijk blah 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 entry is the probability of pi, pj, pk, and so on. Okay, it's a probability that a given batch has the first element being I, the second element being j, and so on. Okay, so what's special about this? Well, this is a rank 1 k-tensor. Okay, corresponds to this distribution over k-tuples. Okay, so the intuition for why the error of recovery should decrease as the square root of the batch size is just the following. So if you have two distributions, p and q, whose distance is epsilon, and you look at how different the corresponding k-tensors are, well, in this k-tensor land, basically their distance will be blown up by a factor of root k. Okay, so so p is a distribution over outcomes. The k-tensor is a distribution over a set of k samples. Okay. And this will blow up your distance by a root k factor, which will end up kind of, yeah, sorry.
So the difference between a set and a list isn't important for this?
Yeah, just to keep everything nice, let's just think about it as a batch is a list instead of a set. Yeah. Okay, maybe I'll skip this. It's pretty easy to show that you get this root k. And the key is really to think about this in the case where the distribution is over zeros and ones. Okay. And yeah, it's kind of an exercise that you guys could all do in 20 minutes. Okay, so the idea for kind of this root k is really that if you ignore the sample complexity and all that, if the true distribution is, say, p, and the adversary wants to fool you into outputting something q, whose distance is, say, some epsilon prime, then it really needs to control at least the epsilon prime times square root k portion of the probability mass in this empirical thing that you view. Okay? So if you want to kind of move between two different distributions in this k-tensor land, you need to control an extra root k fraction of the mass. Okay? So that's all that's there. Okay, let me tell you a little bit about this more efficient algorithm. So it's not that efficient. The runtime is polynomial in the distribution domain to the k. Okay. So what you observe, so imagine you have tons of data. So you observe this kind of empirical k-tensor. This is the empirical distribution of all the batches you see. What is it? Well, it's 1 minus epsilon times the good stuff, plus some epsilon times some garbage. Okay, and this good stuff is a rank 1 k-tensor. It's really nice. The garbage, who knows what it is, but it's non-negative. Okay, the extra data is not going to take away anything from this. It can only add. Okay, so algorithmically, any of the following things would be fine. If we just take A and we return some low rank approximation, so some rank 1 approximation to A, that's good in a kind of L1 element-wise sense, then we would be fine. Of course, that problem is hard. Okay, so even in the matrix case, even in the matrix case when k is 2, getting these L1 accurate estimates, well, it's NP hard, although there's a recent approximation algorithm for that. Once you get k equals 3, you're in tensor world, and now all of these approximation things are hard. There are connections to planted clique. This seems like a quite hard problem, even finding something close to the best rank 1 approximation. Okay, well, yeah. 2 minutes, 1 minute? 2, okay. Okay, however, in our setting, we get extremely lucky for a slightly mysterious reason. At least it's mysterious to me. I imagine Mingda understands it better. And basically, the case is the following. So I give you a matrix A that has this form. It's 1 minus epsilon times some nice rank 1 thing plus some non-negative noise. And the idea is basically one of two things happens. Either the adversary has spread the mass out fairly uniformly. So either B is fairly uniform, in which case, no big deal. It doesn't matter that it's there. Okay, the empirical distribution will still be fine. The other case is that this empirical distribution, B, is very, the other case is where B is far from uniform. In some sense, it must have some structure. But in that case, it actually turns out that the fact that B has some concentrated stuff somewhere means that some of its rows or columns or rods must actually be very, very lightweight. Okay? So the algorithm is basically the following. You're basically just going to check each of the rows and columns and rods and so on of A and see if each of these candidates gives rise to something like a good rank 1 approximation in this L1 sense of what you see. Okay? So it's this kind of cool thing that, in our case, we're very lucky that the answer must be somewhere inside what you observe, and you just need to kind of guess and check. And anyway, so we get quite lucky. So, so at least the algorithm, the runtime is polynomial in the size of this K-tensor. Okay, which is what the usual goal is in some of these tensor low-rank recovery problems. Okay, so going forward. So there are some nice specific technical questions. So one question is, can you get a fully polynomial runtime, polynomial in n and k and so on, that achieves this optimal epsilon over square root batch size recovery? I think the model here is very close to the practical problem people care about, and it would be worthwhile to get, say, a practically implementable heuristic for this. If getting a fully polynomial thing that achieves the epsilon over root k is hard, you could also ask, well, what's the best recovery guarantee you could hope for via fully polynomial time algorithm? So these are concrete questions. I have some thoughts about them. I think they're great. Slightly more broadly, there are many related questions that are, along these lines that are theoretically rich. They seem very practically relevant, particularly given all this discussion over federated learning. And many of them are pretty open, both from practical and a theory perspective. Okay, anyway, so maybe I'll leave it at that. Thanks. Yeah, so this is, let's see, well, yeah, this is something I guess we were thinking about a little bit now. Yeah, maybe we can talk about it after this. But yeah, I mean, there's nothing that's succinctly statable.